So why does this matter? If two computers are going to communicate, they need to agree on whether they represent numbers using big endian or little endian formats. This is complicated by the fact that different processors use different endianness. For example, x86 processors from Intel and AMD are little endian. The least significant byte comes first. ARM processors, in contrast, such as those used in the iPhone, are big endian, where the most significant byte comes first. We don't want two computers to care or know whether the other side is big endian or little endian. So protocol specification bodies typically pick one and stick with it. For the internet, this means big endian. All protocols that are internet specifications use a big endian format. Here's an example snippet of C code that will tell you whether your computer is big endian or little endian. It takes a 16-byte value and casts a pointer to it that lets the code look at the bytes individually. If the byte at index 0 is 0x40, this means the most significant byte comes first and the computer is big endian. If the byte at index 1 is 0x40, then it's little endian. Well, wait, this creates a complication. You need an internet packet to be in big endian format, but what if your processor is little endian? Let's say, for example, that you want to set the port number of a TCP segment to be 80, the HTTP port. A simple way to do this might be to create a C struct that has a field port at the right offset. But if you use a value 80 to compare with the port field, that 80 will be stored little endian, with 0x50 as the first byte. Big endian needs 0x50 stored in the second byte. So although the port field in the segment is 80, and you have 80 as your value, this test will fail. To make this easier, C networking libraries provide utility functions that convert between host and network order. The function h2ns, for example, takes a host short, 16-bit value, as a parameter and returns a value in network order. There's also functions for converting a network short to a host short and functions for longs, 32-bit values. So the right way to test whether the packet port is 80 is to read the port field of the packet structure and call n2hs to convert it from network order to host order. You can then compare it with 80 and get the correct result. In the case of a little endian architecture, n to hs and h to ns reverse the order of the two bytes. In the case of a big endian architecture, they just return the value unchanged. These functions provide you the mechanisms by which you can write networking code that's independent of your processor architecture. But be careful. I really can't stress this enough. Be careful whenever you handle network data. If you aren't principled and rigorous about when you translate between host and network order, you'll give yourself a tremendous headache because you've forgotten to convert or have inadvertently converted twice and suddenly your protocol is behaving wrongly or triggering all kinds of weird bugs. I've certainly done this many times, and so you want to avoid it as much as you can. Now that we know how internet specifications lay out multi-byte values in network order, or big endian, we can look at how internet specifications describe their packet formats. For historical reasons, internet specifications are written in plain ASCII text. The block of text on the left is taken verbatim from Request for Comments RFC 791, which specifies the Internet Protocol version 4, or IPv4. The top shows the bits from 0 to 31. Packets are written 4 bytes wide. Since IPv4 has 5 rows of required fields, this means that an IPv4 header is at least 20 bytes long. Nick and I often use a simpler visual format when we show packets like the one on the right. To use this as an example, the total length field of an IPv4 packet is 2 bytes or 16 bits long, as you can see in the upper right. This means that an IPv4 packet can't be longer than 65,535 bytes. That field in the packet is stored big endian. A packet length of 1400 bytes is stored as 0x578. So the third byte of an IP packet of that length is 0x05. Let's see this in Wireshark. I'm just going to start Wireshark and listen for packets. This first packet is for something called TLS, or Transport Layer Security. It's what web browsers use for secure connections, HTTPS. TLS hides the data of the packet from us, but we can still see its headers. Using Wireshark, we can see that a TLS payload is inside a TCP segment to port 443, the standard TLS port. This TCP segment is inside an IPv4 header. Looking in detail at the IPv4 header, we can see that the packet's total length field is 1230. The hexadecimal for 1230 is 0x04CE, 1024 or 4 times 256 plus 106 or 0xCE. At the bottom, Wireshark shows us the actual bytes of the packet, and there it is, P1204CE in big endian or network order. You've seen how different processors lay out numbers differently, but since network protocols need to agree, protocol specifications decide how the numbers are laid out in their packets, which can differ from your processor. To help you with this, C networking libraries provide helper functions that convert between host and network order, but use them carefully. Using them haphazardly can easily lead you to many lost hours of debugging, which can be prevented by being careful when you start and deciding on a principled approach to converting in your code.